Okay, students, we are now going to consider some specific types of reactions. And these are going to be reactions where the reactant is a single entity, a single component. So let's talk first about first order reactions. Consider this reaction where reactant A is converted to a product or perhaps products. We would say in this case, based on the expression, the equation there, that the rate expression would be rate equals minus the change in concentration of A over time. But because it is a first order reaction, the rate law would be written as rate equals K, the rate constant, times the concentration of A. Notice that in this case, although not written, the exponent, the power of A, is 1, first order. Let's use these equations to find a few things. For example, what would be the units of the rate constant? So if we take that rate law and we rearrange it so that it's rate over concentration of A. Remember, rate is molar units per second, and the concentration is in molarity, which means the molarities cancel out and you end up with units of reciprocal seconds, or seconds to the -1, which you explained earlier. It's another way of writing 1 over S. Now let's take the two expressions we have here for the rate. One, the expression that we derive from measuring the change in concentration of A. The other one, the expression for the rate law. And let's equalize those. So we have minus delta A over delta T equals K times A. I'm not going to expect you all to have already done calculus, but in calculus, you can solve this equation and find an expression that looks like this that we're going to call the integrated rate law. Notice that it uses the natural logarithm function of A, and then you have this expression there. In this integrated rate law, bracketed A would be the concentration of reactant A at any time t, and bracketed A sub 0 would be the concentration of A at time t equals 0. In other words, at the moment that we start measuring the rate of the reaction. Notice that this integrated rate law has the form of a straight line, right? Where if you were to plot the natural logarithm of A versus the time, you would get a straight line where the slope equals minus K, and the intercept on the y-axis would be the natural logarithm of the initial concentration of A, which makes it then very useful in some analysis we're going to do later on. Now, what is this function of the natural logarithm? I think some of you may have forgotten, or perhaps you had never heard of this function. So let me give you a very brief, shallow explanation. It's what I sometimes call the tourist version of an explanation, because it's kind of like just the minimal stuff you need to know in order to communicate it. Okay, so let's go to our document camera. Let's talk a little bit about this function of the natural logarithm, and then we'll come back to our slideshow. Okay, hold on. Okay, let me see if I can give you like a very simple explanation of what the natural logarithm is. Okay, let's start out with a chart. Let's say that we're going to plot the reciprocal of x versus x, and this is the graph that you would obtain. Now, what happens if I were to calculate the area under a certain portion of this curve? All right, let's say that I want to calculate the value from x equals 1 to some value that's going to end up being over here, such that the area under the curve for that span there, right, for that range is going to be equal to 1. So in other words, the area under the curve between x equals 1 and some number we're going to call e, the area under the curve between those two is 1. And this number e is what we call the base of natural logarithms. It was called e for Leonhard Euler, a mathematician from the 18th century. Okay, and essentially, what is the use of this? Well, the idea here is that value of e is actually, e is one of those numbers kind of like pi. It has a number like 2.718281828, etc., etc., etc. One of those infinite numbers like pi that serve a function in many particular applications. In this case, what we're going to say is that let's say that I have a natural logarithm. A natural logarithm is essentially a logarithm where the base is not 10 like we normally use them, but actually e. So if we say that the natural logarithm of a number n equals, let's say, a, what that means is that the base of natural logarithms e to the a equals this value n. So it's very similar to base 10 logarithms. The only difference is that instead of the base of the logarithm being 10, the base of this logarithm function is this magical number e. Now let's remember some rules about working with these things. For example, if I have the natural logarithm of a product between two numbers, x times y, I can also express that as the sum of the natural logarithms of each, right? If I have, on the other hand, the natural logarithm of the ratio of x to y, that can also be written as log of x minus log of y. And another one that's important is that I have a certain logarithm of a number elevated to a certain exponent. That exponent, it can be taken out and say this is the same as n times the natural logarithm of x. Now, what does it all mean? Why do we use this particular function and not the base 10 ones? Well, the reason is that pragmatically, e and the natural logarithms are useful in many applications where we're studying growth or distributions. For example, so this is some applications. If I say e to the x, I can make that to mean what is the amount of growth of, let's say, for example, a let's say an investment portfolio, for example. Amount of growth over time x, for example. That's how we could use that. You can also use the natural logarithm to describe things that, again, have to do with percent growth or percent distributions. You can use it in demographics. You can use it in economics and finance. So it has several applications. So I just wanted to give you a sense, in case you forgot, where we got this value from. And we're going to be applying it to many of these derivations that we're going to be using here in kinetics. Okay? All right. Thanks. Okay, we are back here with our PowerPoint. One of the things that is interesting about this type of format is that it allows us to calculate the value of k purely from a graph. Remember that in other experiments that we discussed, we had the initial rates data, and once we had determined what the rate law was, we would take any one of the data sets and solve for the value of k in those. Now in this case, we are looking at only a single reactant. And so what we can do is, for example, here's a reaction for the compound dinitrogen pentoxide as it decomposes into nitrogen dioxide and oxygen. And here is a graph where you have the natural logarithm of the concentration of N2O5 at different times. And as you can see, it is a straight line. Just a little bit about this compound N2O5 in case you're curious about it. It is typically dissolved in chloroform or carbon tetrachloride, and it's used in several types of organic chemistry reactions. As is the case with many nitrogen-containing compounds, of course, it can be used for making explosives. If you dissolve it in water, you will produce nitric acid. Okay, so anyway, in this case, what we're going to say is we're going to track the quote-unquote disappearance, right, of N2O5 as the reaction proceeds. We want to find the value of K. But instead of using different data sets, we're going to use the graph here. So remember that in a straight line, the slope of the line is the change in the y variable divided by the change in the x variable. So in this case, we have highlighted two data points here, the one for 400 seconds and the one for 2,430 seconds. And we can see the corresponding values of the natural logarithm there. By the way, the natural logarithm is one of those functions where once we apply it, we do not consider it to have any units at all. So let's pick these two data points. So let's take the delta y, that is the difference between the final y and the initial y. So that's minus 1.50 minus negative 0.34. Be careful because as you can see, the scale is running in the negative section here of the values of natural logarithm. And then the corresponding values of x, in other words, of time, would be 2,430 seconds minus 400 seconds, and that one keeps the units in there. We solve this and we get minus 5.7 times 10 to the negative 4 s minus 1, in other words, over per second. And note the units here, okay? Note the units. Now, notice that the slope, which is what we calculated here, is the negative of k for a first order reaction. And so k would be the negative of the slope, which is 5.7 times 10 to the minus 4 inverse seconds. Again, notice the units there. And also notice that the plot is linear, and therefore that is a giveaway that the reaction is first order. Let's use the integrated rate equation in a specific application here. The reaction A converting to B, with A having a coefficient of 2, is first order in A. Remember, the order of the reaction does not necessarily relate to the coefficient of the reactant. With a rate constant of 2.8 times 10 to the negative 2 inverse seconds at 80 degrees Celsius. How long will it take for A to decrease from 0.88 molar to 0.14 molar? So anytime you see a problem where they give you some kind of information, either about the order of the reaction or the rate constant, when you can identify from the units what the order is, and then they ask you questions like, how much time is it going to take for this change to happen? Or, if we start with this amount of stuff, how much will be left after X amount of seconds? Anytime you see those kind of questions, kind of like by default, go to the integrated rate law. So let's see what that is. So this is the format of the integrated rate law, right? Where the initial concentration, in other words, when we start the test here, is 0.88 molar. That's A sub 0. And then A is 0.14 molar. That's our target. And our goal is to find out what is the value of T when we plug in these numbers, right? So let's rearrange the integrated rate law so we can isolate the unknown, which in this case is t. So we have log of a sub 0 minus log of a. We're going to divide that on both sides by k. However, if you remember the rules that I gave you about natural logarithms, we can condense the the numerator of this ratio, log of a sub 0 minus log of a, into log of a sub 0 over a, which will make the calculations simpler. So let's plug in the numbers. We have the numbers given above. You can see how writing it this way, we can see clearly how the units of molarity will cancel out, because as we said, the natural logarithm is a function that should not have any units. The value of k is given to us above, and so all we have to do now is we need to fill in the numbers in the calculator, and we get 66 seconds. That's how long it'll take for the concentration of reactant A to go from 0.88 molar to 0.14 molar. Again, anytime you see problems that have to do with how much is going to change, how long is it going to take, that kind of thing, where both time and concentration are involved, think, I got to use the integrated rate law. As we discussed earlier, sometimes you track the appearance of a product or disappearance of a reactant by tracking the pressure of gases. Let's look again at this form of the integrated rate law. Again, in this case, we subtracted log of a sub 0, and then we kind of like merged the logarithms using the rules of logarithms, and we get this expression. Now, recall the ideal gas law, PV equals nRT, right? Again, if we were to simply isolate N over V, that means that on the other side we have P over RT. But remember, N over V is moles per liter, which means that this is the molarity. Remember, you can only do this for gases, okay? Don't be caught trying to apply the ideal gas law to substances in solution or solids or stuff like that, okay? It doesn't work that way. Okay, so let's put in the integrated rate law in here. Remember, in this case, A is a gas, so the molarity at the end is going to be the final pressure over RT. We assume that the temperature remains constant, and the initial molarity would be the initial pressure over RT. So that means that the RTs are going to cancel out, and you end up with log of PT over 0, and we know that that equals minus KT. So as you can see, if we again expand the logarithm of that fraction into log of PT minus log of P sub 0, and then we move the log of P sub 0 to the right side, we end up with an expression that is totally parallel to the one we derived before, except that in this case, rather than molarities of the reactant, we have its pressure. So it doesn't matter which method you use to figure out the amount, we can still use the same integrated rate law. Another thing that we sometimes discuss in studying these reactions is something called the half-life, T sub 1/2. This is the time required for the concentration of a reactant to decrease to half of its initial concentration. In other words, T sub 1/2 is the value of T when the concentration of A is the initial concentration divided by 2. So if we were to put those values into the integrated rate law and rearrange to solve for T sub 1/2, this is what we would have. In other words, log of initial over the final, which in this case would be initial divided by 2, all of that divided by K. But as you can see up there, the initial concentrations cancel out, and because the 2 is in the denominator of the denominator, we end up with this being natural logarithm of 2 divided by K, and the natural logarithm of 2 is something you can put in the calculator, and to 3 decimal places, it would be 0.693. What is important about this expression is that notice that the half-life for a first order reaction is independent of the initial concentration. In other words, it doesn't matter at which point of the reaction you start measuring. In other words, what's going to be your initial concentration of your test. The half-life is not going to depend on what point in that process you picked. So let's do an example here. Okay, go back to our decomposition of dinitrogen pentoxide. What is the half-life if it decomposes with a rate constant of 5.7 times 10 to the negative 4? I think that may have been the value that we found when we were doing the graphical analysis, right? But let's say that we didn't do that. We're just being given this information. So according to this equation we just derived, the half-life should be the natural log of 2 divided by k, right? Well, let's say that you had not done that graph a couple of slides ago. You just see this for the first time. How do we know that the composition is first order? How do we know that we can use this equation for the half-life? That's right. Remember I told you one of the giveaways of the order of a reaction is the units of the rate constant. The units of k, in other words, 1 over seconds, or seconds to the negative 1, kind of tells you that this is a first order reaction. And therefore, we can use the equation for the half-life, 0.693 divided by k, which is given in there. And notice that the inverse seconds are going to flip up, and we're going to end up with 1200 seconds, which is roughly about 20, well, actually, it's about 20 minutes. So once more, this is another type of calculation that you might be asked to do in your homework and your assignments and your practice exercises. Okay. Again, let me tell you, feel free to stop the video and go back through all these to make sure you understand them. I'm jumping over the calculations, so go ahead and use your calculator. Get familiarized with it, especially how do you put logarithms in your calculator. Some calculators, you put the number and then click a button that says ln. Some of them, the ln function is an alternate one, so you have to go to an alternate or secondary set of controls. And in other calculators, you put the function first, and then you have a parenthesis, and you put the number inside that parenthesis. So make sure you know how to work your calculator for doing these natural logarithms. All right, now let's look at another view of these first order reactions, and that is, what if I were to plot, for example, the decay or the decomposition or the conversion of this reactant A over time, and let's say that I specifically mark out the half-lives. In other words, what I want to do is the number of half-lives that have passed and what is the concentration of A. So remember, when this whole thing starts, you have an initial concentration, which is A sub 0. After one half-life, you would have A sub 0 divided by 2, so 1/2 of the initial concentration. Now, if you let another half-life pass, and in this case, apparently the half-life is 1 minute, so if you let one more minute pass, one more half-life, you are now at 1/2 of 1/2, in other words, a quarter of the initial concentration. Let's give it one more half-life, one more minute. That would be 1/2 of 1/2 of 1/2, so that would be 1/8 of the initial concentration. And you can see where we're going with this, right? Because the half-life is constant in a first order reaction, you can simply count the progress of the reaction, not by maybe following the actual concentration, but by counting the number of half-lives. Notice that at any number n of half-lives, there is going to be A sub 0 divided by 2 to the n reactant left. Look at that table we just did there with the number of half-lives and convince yourself that that equation is correct, okay? Great. Okay, let's look now at second order reactions, and we're gonna go a little faster over this one because the analysis is the same. The only thing that's gonna change is the equations that we arrive at and the units. So again, this is an equation where you have reactant being converted to product, and the rate is going to be minus the change in reactant over time. The difference here is that the rate law is second order. In other words, it's K times A squared. All right, that's the difference. This is a second order reaction. So using that rate law over there, let's go ahead and find out what are the units of K. So solving for K, we have rate over A squared. Remember, rate is molar units per second. And now A squared would be molarity squared, which means that only one of the molarity units gets canceled out. The other one is left in the bottom. So we essentially have 1 over molar units per second, or m to the minus 1 times s to the minus 1. And if you are given a rate constant with these types of units, it tells you the reaction must be second order. Like we did before, let's equalize the two expressions of the rate, the one from what you measure and the one from the rate law. And once more, we can apply calculus to this and arrive at an integrated rate law. Those of you who have taken integral calculus already will be able to solve that equation. And we end up with this expression here. 1 over A equals KT plus 1 over A sub 0, where A is the concentration of A at any time, and A sub 0 is the concentration of A at time equals 0, or essentially the point at which we started to measure the reaction rate. Notice that this one also has the form of a straight line, except that in this case, the slope is positive and equal to the rate constant. The intercept on the y-axis is 1 over the initial concentration. So a reaction that you plot out 1 over A versus T, and it gives you a straight line, tells you that that reaction must have been second order. Let's talk about the half-life. Again, this is the time at which the concentration of A is exactly 1/2 of the initial concentration. I'm not going to bother you with a lot of derivations here. What we find is that the half-life is 1 over K times the initial concentration. Notice that unlike the first order reactions, in this case, the half-life is dependent on the initial concentration. So in other words, the half-life is not a constant. It depends on when you started to measure the process. The last set of reactions we're going to consider here are the zero order reactions. As we will see later on in the unit, there is a meaning to this, zero, first, second order reactions. There is a meaning in terms of what we call mechanisms of reactions, okay? So there is a reason, therefore, why we're only going to consider, first, second, and zero order. By the way, some textbooks will call this zeroth order with a th at the end. I have a hard time pronouncing that, I'm sorry. So I'm going to call it zero order, okay? Once more, we have A converted to a product. We have the expression for the rate as we measure it. And in this case, the rate law, be careful. Zero order doesn't mean that the rate is 0. It means that the exponent on the A is 0, but since A to the 0 equals 1, that means that the rate equals K. In other words, for zero order reactions, what we're saying is that the rate is constant. The rate is constant. Let's look again at this rate law and notice that in this case, the K is equal to the rate divided by, A to the 0 power, but that's 1. So in other words, K has the same units as the rate, molar units per second. Let's combine the two expressions of the rate, the one from the experimental data, the one from the rate law. And once more, let's apply calculus and integrate this to solve it and get an integrated rate law. And the expression we're going to get is this one. A equals minus KT plus A sub 0. Again, A is the concentration at any time t. A sub 0 is the initial concentration, the concentration of A at time t equals 0. And once more, if we want to do a graph, if we graph the concentration of A versus T, we get a straight line with a negative slope that is equal to minus K. Careful when you do solving all these things. Don't forget these negative signs. You know, don't get misled by those. The half-life, again, is the time at which the concentration is half of the initial concentration. If we plug those values into the integrated rate law and solve for the half-life, we find that it's going to be initial A over 2K. In other words, once more, the half-life is dependent on the initial concentration. The half-life, in this case, is not constant. Okay, this is a table that you'll find in your textbooks. Now, it says here table 14.2. I think a lot of this is from TRO, and it's going to depend on which edition of TRO you have. So in your edition of TRO, this table might be 14.2, it might be 15.2. If you are using the Top Hat text, they should have a table similar to this, but I don't know what the number is. I believe in their case, the kinetics chapter is 13. But what I would do is take this slide and maybe print it or save it as a separate thing and have it with you at all times when you're solving problems. Notice that it gives you, for each order of reaction, 0, first, or second, what is the rate law, what are the units of K, what is the integrated rate law, what kind of plot gives you a straight line, and what is the expression of the half-life. So this is a very useful table that essentially blends in everything we've been talking about for the past few minutes. Let's close out by doing a little practice exercise. Here's a reaction C4H8 being converted into C2H4. Later in the semester, we'll learn more about these kinds of compounds. They're called organic compounds. Specifically, they're called alkanes or hydrocarbons sometimes. Okay, so hydrocarbons, I'm sorry, because I'm not alkane, necessarily alkanes. Anyway, the data here shows you the pressure of the reactant C4H8 at different times. And you can see it is given in millimeters of mercury, or torr. And as you can see, as time progresses, the pressure decreases because the gas is being consumed. It's being depleted. So questions that you're going to be asked in this case is, what is the order of the reaction and what is the rate constant? So the strategy here is, remember, according to our previous slide, we have 3 alternatives and each one has a specific type of graph that will give you a straight line. So if we plot simply the pressure of reactant versus time just as it is, we are testing in this case to see if the reaction is 0 order. See how a graph of A versus T will give you a straight line? So if that set of data alone gives you a straight line, it means that the reaction is probably, or most likely, 0 order. But we have to be able to test the other 2 possibilities. So we're going to need to do a graph of the natural logarithm of the pressure versus time, so we can test for first order, and one of the reciprocal of the pressure versus time, so we can test for second order. So in the next set of columns, what I've done is, first, I have taken the natural logarithm of the pressure for each one of those values in there. And in the next one, I have taken the reciprocal of the pressure for each one of those numbers there. And what I'm going to do now is I'm going to go to my Excel program and I'm going to draw graphs of each set of data. So it'll be pressure versus time, natural log of pressure versus time, 1 over pressure versus time. And we're going to test each one of those. Let's start out with the test for 0 order, which would be pressure versus time. And that's the one we have here. Okay. Notice that it's giving me a curve. You know, it doesn't change a whole lot, but it is still a curve. Let's see if the other ones work better. Let's try the log of the pressure versus time. This is the test for first order. There we go. And I went ahead and put in the equation of the line, which Excel will give you. We'll talk a little bit about that in a few moments. And the last test would be the reciprocal of pressure versus time. Notice that this one is also giving us a curved graph. So of the three, which one gave us the best fit to a straight line? That's right, the graph that had the log of p versus time. And what this does also is it gives us the equation of the line. It says y equals minus 1.19 e to the minus 4 means 10 to the minus 4 times x. So that is the slope of this line. And we can say that the reaction is first order, and k would be minus the slope, which is 1.19 times 10 to the 4. Proper order, proper units for a first order reaction is s to the minus 1, or inverse seconds. Now, in one of your first exercises in our lab sections, you're going to be given a set of data very similar to this one, and your task is going to be to use the Microsoft Excel software to draw the graphs and arrive at the same conclusions. What is the order of the reaction, and what is the value of K for a reaction we're going to give you in there, okay? If you're not familiar with drawing graphs in Excel, I have placed a little video in the Before We Begin section of our Canvas page. And don't worry, in the activity you're going to do, we're going to give you a good explanation and step-by-step directions in how to draw your graphs, okay? So, very good. Next time, we're going to continue on this topic of kinetics, but we're going to start talking about the energy components of a chemical reaction, and we're going to come up with a theory, a model, to explain why and how chemical reactions happen. Okay, so I'll see you then. Have a good time. Thank you very much.